Last time, we talked about Euler paths, tracing every edge of a graph exactly once without repeating. But what if you need to start and end at the same place? That's called an Euler circuit, and they're integral to city planning. Euler circuits are always Euler paths, but not all Euler paths are Euler circuits. So how do you know if a connected graph qualifies? Easy rule. If even one vertex has an odd degree, boom, no Euler circuit. If every vertex is even, congrats, there's an Euler circuit somewhere in your graph. Finding the actual circuit takes a little strategy, but we can reuse Fleury's algorithm from before. First, confirm that your graph has an Euler path. If it doesn't, you can Eulerize it. I'll talk about that later, so for now, just start wherever. Then, choose any edge to add to your circuit as long as deleting the edge doesn't split the graph into two disconnected parts. The real-world applications of this are way more interesting than just tracing a shape, though. Imagine a neighborhood made of 3 blocks with mailboxes along these streets. We can model this as a graph. Each street corner is a vertex, each street with mailboxes is an edge. Simple. Now, suppose our mail carrier wants to start and end at vertex A, covering every street exactly once. But when we check the degree of the vertices, we spot two odd degree vertices, which means there's no Euler circuit in this graph. But do we give up? Of course not. We can add extra edges to force the graph into compliance, which is called Eulerizing the graph. If we duplicate the edge between C and F, every vertex becomes even, and now we can find an Euler circuit. Sure, it's not 100% perfect. The mail carrier will have to retrace that one duplicated edge, but doubling back once is way better than wandering randomly and wasting time and money. Eulerizing is strategically adding just enough extra paths to make the route efficient. So how do we know which edges to duplicate? How is one way better than the other? Take this diamond-shaped hiking trail with a bridge in the middle. You start at your campsite, and your goal is to walk every part of the trail once, ideally without taking the same path twice, and end back at your campsite. We can represent this with a graph, like this, with your campsite being vertex A. Because you watch my videos, you notice that you're looking for an Euler circuit in a graph with two odd degree vertices, so you know you have to Eulerize the graph. You duplicate these two edges, AB and AC, and take this path. While this path works, it isn't the best path you can take. This Eulerization requires you to double back twice, but there's a way to only double back once. Can you find it? If you walk the bridge twice, that properly and ideally Eulerizes the graph. It's better than the other way because you only add one extra edge. This idea is part of a well-studied concept in management science called the Chinese postman problem. Basically, how do you cover every path with the least amount of backtracking? It might seem overkill for a hiking trail, but scale this up to entire neighborhoods or cities, and suddenly it's $1 million question. Because a bad Eulerization means your route isn't as efficient as it could be. So a street sweeper burns extra fuel, a mail carrier wastes more time doubling back, and so on. One bad Eulerization might waste only a little bit each day, but over years and years that compounds into huge losses, especially over multiple routes.